In this video, we're going to look at a couple examples of how to solve a system of equations by the substitution method. So our first example, we're going to have 3x plus 4y equals 23. And our second example is going to be y equals 12 minus 7x. So this system is already set up for us to do substitution. Remember that we want one of our two equations to be set up as x equals or y equals. We have that with our second equation here. So since we have y equals 12 minus 7x is the same as y, and so we're going to replace the y here in our first equation with 12 minus 7x. And that way it's going to give us just one equation with one variable, so we can solve for that and work our way towards the full solution. So our second equation, or excuse me, our first equation can now be rewritten so that we plug in 12 minus 7x for the y, and now we just see one variable. So now we just have to combine our x terms and solve for x, go from there. Let's see that we can distribute here. So I want to simplify my equation a bit. I've got two x terms here. I'm going to combine those. And now I see I've got a constant on both sides of my equation. So I want to subtract that 48 over to the right side, slowly getting x by itself. And this one works out nice. A lot of times when you have big numbers, negatives, fractions, it does end up working out nice at the end. Well, negative 25 divided by itself is 1. So there's the first half of our solution. And now since I'm trying to solve for y, I could plug 1 into either of my original equations. But because we've got y equals 12 minus 7x here with my second equation, I can just plug 1 in and substitute for x there. And I'm going to have a couple less steps. It's nice that we've got just a 1 there. We don't have to do too much math. We get y equals 5. So our equation, our solution to our system should be 1, 5. Now, if we want to double check our work, well, we know that 1, 5 is in the second equation, that it works there, because that's how we got the 5, using the second equation. So if I want to double check that this is the right solution and it fits in both lines, then I need to plug it into my first equation. So let's go ahead and do that. We got 3x plus 4y equals 23. So I'm going to substitute those in just to make sure that this equation works with my point 1, 5. And I end up with 3 plus 20. And that does in fact hold true. So 1, 5 is my correct answer. Looking at another example, we've got y equals 3 over 2x plus 2. 3x minus 2y equals negative 4. Well, my first equation is set up as y equals, similar to our first example. So I'm going to substitute that piece in for y in our other equation. So once again, we are kind of getting rid of the y variable and just narrowing it down to one equation. And now we can solve for x. So first step is I need to distribute that negative 2. Well, negative 2 times 3 over 2, the 2's cancel, right? It's like 2 over 1 times 3 over 2. And so it's going to simplify to negative 3x, and then negative 2 times 2 gives us negative 4. Well, I notice that my x's, when I go to combine those, they actually cancel each other, and they just give us 0. So that cancels, and all I'm left with is negative 4 equal to negative 4. So it doesn't give me a value for x, which means that there's not just one solution. Okay, so there's two different scenarios we have here if the variables completely cancel each other out. In this case, negative 4 does equal negative 4. So this is an example of two lines that are the exact same. So it's the same line, just written two different ways with our original equations up here. So this is an example where our lines completely overlap, and we have an infinite number of solutions because every point on one line is matches up with every point on the other line. Now, if you end up with two numbers that do not equal each other, well, that's not true, and so the equations are going to be parallel, and that tells us that there's no solution. So those are the two exceptions if we've got an equation here where the variables end up totally canceling each other out.